Rn. Sorry, SLn minus 1. So we direct Rn minus 1 over the z points of that same thing. Somehow for n equals 2, this part vanishes and we stay just with R mod z. So this is a bit misleading. Now, SL2R mod SL2Z is already non-compact. The fibers will not be compact. And there will be no group structure to them. So this is a bit mysterious. Maybe you should think to yourself, what is this actual action of the circle of that space? It is not something very natural. In a sense, it exists, but it is not very natural, and indeed it does not extend to a higher dimension, this phenomenon. This is not a group anymore. But the fibers are non-compact, but they do have finite measure. On them by induction. I mean, think of n equals 3. We just proved that SL2Z is a lattice in SL2R. So this is basically SL2R modulo SL2Z times, measure-wise, R2 mod Z2. It's the same. And there is a natural invariant finite measure on it. So even though when you take a completely supported function on here and you lift it, you don't get a completely supported function. But if you take a completely supported function, actually if you take an L1 function over here, and you lift it, just pull back, it is still L1. Because you just integrated over those finite fibers, measure-wise finite. And you can push again. So this I don't want to do in details, but it's not much harder than what we've been so far. I decided to use this properties just to facilitate the introduction. But on them, hence, you do get, or Ziegler do get.
So could you do one more step?
Just a minute, just write it down, yes. Ziegler does get the transform L1 R2, Rn, sorry, to L1 Xn. I'll just finish the sentence, and the proof just goes on. The same. Minkowski theorem works for every dimension. And actually, I guess I should try to keep the n here, or something like that, and it goes just the same, and the proof continues, and by induction you get by induction, SLN Z is a lattice in SLN R. This is my first remark, and I'm yes.
So I understand that this Markov here is already embedded.
Yes, this is embedded.
From L1 into L1 over Y. But then you are taking this summation over gamma orbits. Why does this work?
Okay, so there is something. I don't know it in details. I agree. I don't give you all details, but it works. No, just a minute. By this finiteness of fibers, when you take a function, an L1 function here, what is non-trivial that when you pull back, somehow when you pull back functions, the L1ness of them is not preserved. You should pull back, I don't know, at infinity functions. But you can always push down L1 functions. So if you take L1 function, it is not clear that you will get L1 function here, but this is by induction. And then when you take an L1 function here, maybe you should think of L1 functions as absolutely continuous measures, probability measures, or finite measures on space. You can always push them, push measures. So the concept of pushing L1 functions is well defined, in general. Okay, so this is not an issue. Sorry, okay, so this term that I did give you can be pretty easily be transferred into a general proof that SLNZ is a lattice in SLNR, and but let me continue my historical remarks. So if you take Minkowski theorem and you replace it with a slightly more delicate Poisson summation argument, which again I've chosen not to do, but you can actually get the exact up-to-natural normalization volume. Can get exact volume. And again, there is some natural normalization involved. And the volume of SLN, the volume of XN will be Z of 2 times Z of 3 times Z of 8. So actually, the right normalization from any point of view will be not the one that makes the Poisson transform, the version of Ziegler transform that I gave you in isometry, but take just the same transform, but sum not over primitive vectors, but over all non-zero vectors. And then this will give you, and then by this consideration that I made, Lebesgue measure on one hand side, give you natural measure on the other hand side, and it will give you that volume, which fits with other. Well, I said enough about this. Now, before I finish, I do want to finish and give a break, but. Another proof for n equals 2 could be given by estimating, and now I'll put a picture that I will explain in the next hour, estimating the volume of that for the meta domain. If you haven't seen this before, I will explain this. And one can estimate it precisely, or one can estimate it imprecisely, in fact, by just integrating that slightly bigger domain. And this is...
Why? It's easy to integrate exactly.
I'll explain more. Yes, it is easy to integrate it exactly, and I will explain this as well. Again, but now I'm kind of jumping over my head because I didn't introduce that domain yet, and this is on the historical remark level. And this is more or less like by integrating 1 over y squared. This is a domain in some hyperbolic plane, and there is an hyperbolic natural volume here associated, and you can integrate in that slightly bigger domain. I'm saying it because this method can be generalized. That piece, that squarish piece, is called a Ziegler domain. This is And that method, which corresponds to the composition of G, K, and now you take A only, this is from some T, the N, I know. I'm putting some symbols on the board, and these are not very important here. But I just want to say that this kind of method could be generalized to any group using standard group decompositions. And this process is called reduction theory, and it brings a theorem. If one does it precisely, you get to prove the following theorem by Borel and Harishchandra. GZ, if you take, is always a lattice in GR. Is lattice. For semi-simple. So one can generalize it in a more delicate, one needs some geometry of symmetric space, which in our case is the geometry of the hyperbolic plane, in order to do this, or use various group decompositions, and one can kind of look at the cusp of some fundamental domains and integrate over them and get out with it and prove a more general theorem. We proved that GZ is a lattice in GR for SLN. But this can be generalized, but just to get Gauss satisfied and end up this talk, precisely for that fundamental domain, give a picture. And again, sorry if you haven't seen this before, this will be more familiar in a minute. If you take this, I can cut it into half and move to the disk model and take this ideal triangle which has volume pi, area pi, and do this and find this half, or this 1/6 of that triangle is the same as this 1/2 of that fundamental domain, and I don't need actually any integration to say that the volume here is pi over 6. So the volume here is pi over 3. Hence finite. But finite with respect to a different normalization. It doesn't get to pi square over 6. If it does get to 2/3 pi. Never mind. I think